Welcome back, folks. This is the transition lecture that you've been waiting for. Today, we'll start with the ideal transformer. Actually, just a quick review. Then we'll move on to real-world transformers. And finally, we'll get to motors. There were only a few things you needed to know about the ideal transformer. There was the turns ratio, which is the number of turns on the primary divided by the number of turns of the secondary, is equal to the voltage ratio, which is the voltage on the primary over the voltage on the secondary, and that is equal to the current ratio. I think I've reminded you many times to be careful about this because you'll notice this is the primary, but the current is upside down. You see, that's the secondary in the numerator. There were two other things you needed to know. The power, which is to say the complex power in the primary, is equal to the complex power in the secondary. And then there was this other property where the impedance that's reflected through the transformer, this Z prime, is the turns ratio squared multiplied by the impedance of the load. For example, if we have a transformer with a 4:1 turns ratio and a load we can, using this property, reflect this load through or to the other side of the transformer as the turns ratio squared. Since the turns ratio is 4:1, we can take every load and move it to the primary of the transformer by multiplying by 16, which is the turns ratio squared. So if you are an observer here, you would see not 2 ohms, but 32 ohms. You would see not J10, but J160. You would see not this 10 ohm resistor, but you would see a 160 ohm resistor. Again, we've taken this load and we've transferred it to the other side of the transformer. We got rid of the transformer because of this property where we multiplied by the turns ratio squared. An observer looking into these circuits cannot tell that circuit from that circuit. They appear identical. Remember, these properties are true only for an ideal transformer, where the power in is equal to the power out. Real-world transformers are not quite so good. In the real world, we have a power going into the transformer, we have a power leaving the transformer, and then we have losses along the way. We have I squared R losses in the primary winding, we have what are called core loss, and we have I squared R losses in the secondary. You should know that all of these losses manifest as a heating of the transformer. I believe we've talked about efficiency before, where we use the Greek letter eta and declare that efficiency is the ratio of power out to power in. You could also say efficiency is equal to the ratio of the output power over the power out plus the power that's lost. Of course, when you put these two together, the power out plus the power lost is equal to the power in. Before we move on, there's a great big sidebar that you need to pay attention to. When we talk about power, we are talking about the base of the power triangle. We're talking about real power. So remember that. Anytime you see this power flow diagram, this is power. It's P, real power. It's real power that's lost in the primary, in the core, and in the secondary windings. Here's an example. We're told that this is a real-world transformer. It is operating with a full load, so we can assume that power triangle has 50 kVA. We're told the power factor is 80%, which means this is 36.9 degrees. Shift inverse cosine 0.8. Yep, 36.9 degrees. And we're told that the efficiency is 95%. We're going to need the real power. 50 at a phase angle of inverse cosine 0.8 gives us 40 kW and 30 kVAR. Complex power is equal to 50 kVA at a phase angle of 36.9 degrees. We could also say complex power is 40 plus J 30 kVA. And again, this is the real part. We are only interested in the real part when we're dealing with power and efficiency. Eta is equal to power out over power in. In this example, eta is equal to 0.95. Our real power out is 40 kW, and we're asked to find the power in. So that power in is equal to 40 divided by 0.95. Gives us a real power of 41.2 kW. The power flow diagram looks something like this, where we have 41.2 kW entering, 40 kW leaving, which must mean we lost about 1.2 kW along the way. Actually, I should be a little more careful with our words. We didn't lose it along the way. We lost it to the transformer itself. The transformer got hot due to I squared R losses and to core losses. If we wanted to be more precise, we would have a model of the transformer. Here's how we think about this model. Assume this is the ideal transformer that we have always been talking about. To that ideal transformer, we add two pieces. We add this piece, which represents the wire, and we add this piece, which represents the core. The wire, well, think of it this way. The transformer has windings of wire. By virtue of being real-world wire, there will be some resistance associated with that wire. We call this resistance equivalent. So that's the equivalent resistance when we consider both the primary and the secondary winding. What we've done is we've taken this resistance out here, which would have been the secondary, and we've reflected it back to the primary, and we've called it the equivalent resistance. That way we can simplify our calculations. As a similar thought, we have inductance in the secondary. We've taken that inductance, we've reflected it over to the other side, and then we've combined the primary and the secondary to come up with an equivalent number representing both primary and secondary. This branch represents the core, and this resistor is kind of interesting because it's not really a resistor. There is no resistor in the core to speak of. However, there are what are called magnetic domains. You could think of the magnetic domains as a series of vectors that are pointing in different directions. Initially, these magnetic domains are randomly oriented. However, when you apply a magnetic field, they tend to line up in the same direction. It turns out that this operation, this changing of things that are random to changing things that are all in alignment, takes energy. It takes even more energy when we consider that this is alternating current. So at one point in the sinusoid, we need them all to be lined up one direction, and then at some point later, we need them to flip direction. Right? So that might correspond to the positive half cycle, and this corresponds to the negative half cycle. So again, you have all these magnetic domains, and you have to flip them back and forth. That takes energy, and that energy loss is represented by an equivalent resistance. Finally, this reactance is representative of the magnetic energy that is stored in the core. As we move forward, just remember that this is the core, and this piece represents what's happening in the wire. That transformer model we just looked at can be attributed to this fella. This is Charles Proteus Steinmetz, otherwise known as the Wizard of Schenectady. You should know that he developed the transformer model. In fact, he developed all of the phasor notation that we've been using up to this point. And he also developed a model for the induction motor, which looks remarkably like the transformer model. So if you learn the transformer, you also learn how the induction motor operates, or at least how it can be modeled so that you better understand how it works. Let's work one example using the transformer model. This represents the wire in the primary, the wire in the secondary, the core loss, the load, the turns ratio, and we'll let this have a voltage of 277 volts as measured at the load. Speaking of the load, we'll start with the power triangle. So that's 10 kVA at a power factor of 87%. So that's 36.9 degrees with 8 kW here and 6 kVARs here. We could start our problem here. We could say something like the voltage at the load is equal to 277. The power at the load is equal to 10 kVA at a phase angle of 36.9 degrees. We could move on. We could calculate the current here. Then we could back up to this point in the circuit. And knowing all of those things, we could calculate the voltage on the secondary of the transformer. And there's nothing wrong with that. It would certainly work, but it's a lot of work. There's an easier way. What if we took all this and we reflected it across the transformer? That's where that impedance I kept telling you about comes to play. So the impedance on the primary would be the turns ratio squared by the impedance on the secondary, which means we can redraw the circuit to look something like this. This piece, by the way, is the core. So what we're going to do is we're going to take this parallel circuit and we're going to transform it into a series circuit to make the calculations a little bit easier. To do that, you go 200 invert plus 40J invert equals invert equals. So that is 7.69K and J 38.5K. The inductor, by the turns ratio squared, ends up here. So that's 0.12 times 45 times 45. which gives us J 243. The resistor comes across as the turns ratio squared and ends up here. 0.3 times 45 times 45. That's 60.8 ohms. The power is reflected across the transformer. So that's 10 kVA at a phase angle of 36.9 degrees. Voltage is the last thing to worry about. And by the turns ratio, the voltage comes across as 277 times 45. So 12.47 kV. This certainly looks like a mean problem, but consider this. You have performed this operation multiple times. You know how to do that problem. You can find the voltage here, and you can find the current. That shouldn't be a problem. Once you have the voltage and current, you're going to need to calculate the current that's flowing in the core. From there, you're going to have to use Kirchhoff's voltage law and say that the current on the input is equal to the summation of these two. So keep that in mind. So we've got the current on the load, and we've got the current in the core. That gives us the current on the input. Of course, those are all vectors. Starting here, the voltage on the load is 12.47 kV. The current on the load, actually the complex conjugate of the current on the load, is 10 kVA at a phase angle of 36.9 degrees over 12,470. The current is therefore about 802 milliamps at a phase angle of negative 36.9 degrees. You'll notice I'm taking the complex conjugate of what's on the calculator here. So that's where this negative came from. We now move our attention here, and the voltage at that point, we're going to call it voltage X, is equal to 12,470 plus 0.802 angle negative 36.9 by 60.8 plus J243, where we have a current and we have the impedance. Okay, so there's our current, and we're going to multiply that by 60.8 plus 243J, and then we're going to add 12,470. That's 12.6 kV at a phase angle of 0.57 degrees. That brings us here. We know what this current is. We know what the voltage at this point is. What we need now is the current that's in the core. From there, we calculate this current, and finally, we can calculate the input voltage. The current in the core is equal to 12.6 kV at a phase angle of 0.57 divided by 7.7 plus J 38.5 K. So our current in the core is 321 milliamps at a phase angle of negative 78.1 degrees, which means we know this current and we know this current. Using Kirchhoff's current law, we'll take the summation of those two. where the goes intos and the goes out of are equal. Our input current is equal to the current in the core plus the current that's going to the load. So our core was here, and our current in the load was here. So it looks like we already have the core in the calculator. So we're going to add 0.802 at a phase angle of negative 36.9 degrees. Looks like our input current is 1.06 amps at a phase angle of negative 48.4 degrees. We go back up here. We now know the voltage here. We know the current. We can calculate the voltage on the input. So that brings us down this way. The voltage on the input is the voltage at point X. So that's 12.6 K at a phase angle of 0.57 plus our current all multiplied by this. So there's our current multiplied by 10 plus 100J plus 12,600 at a very small phase angle. So that's 12.7 kilovolts at a phase angle of 0.84 degrees. And our current in is right there. If you put those two together, complex power is VI complex conjugate. We would say that the input power is 12.7 at a phase angle of 0.84 by 1.06 at a phase angle of negative 48.4 degrees. Except it's not that because we need the complex conjugate. So it's 1.06 at an angle of 48.4. The voltage is already in our calculator, so we're going to multiply that by the complex conjugate of the current, which gives us 8.78 plus J 10.2 kVA. All that work, all of that writing, just to find out that 8.78 kW went into the transformer. And, where was it? 8 kW came out. If we were to make a power flow diagram, it would look something like this. With 8 kW coming out and about 8.78 kW going in. There's an I squared R loss in the primary, a core loss, and an I squared R loss in the secondary. Let's see if we can put some real numbers on that and see if the output plus the power that's lost is equal to the input. The hardest part of this will be finding the actual current and resistance. It's somewhere up here. We are concerned with the current in the secondary across that resistor, because that will be the real power. Here's the current, and there's the resistor. We'll enter that as 0.802 squared multiplied by 60.8. We'll write that down here as 39 watts lost to the secondary winding. The core, let's see if we can find that. We have a 7.7K resistor, and somewhere, there it is, there's the current flowing through that resistor. We enter that as 7690 multiplied by 0.802 321 squared. Come down here. That's 790 watts lost to the core. And the last thing is the I squared R loss in the primary. So there's the resistor. We just need to find the current. And I believe that was right here. So 1.06 squared multiplied by 10. So about 11 watts lost to the winding. If we add that up, 8,000 plus 39 plus 790 plus 11 should equal pretty close to 8.78. And it's certainly within rounding errors. The efficiency of this transformer is 8,000 divided by 8780. So that's 8,000 divided by 8780. It's about 91%. As a side note, this transformer is not operating at 100% power. Which means if we were to increase the load slightly, we could expect the efficiency to come up a little bit. The thinking goes something like this. If this is efficiency and this is percent load, we have a curve that looks like this, where there is a peak efficiency at some load. As a car analogy, this is you idling in the parking lot. How efficient is your car when it idles? It's not. You're not getting any miles for the fuel that you're using. This point is where your car is most efficient. Sure, it may be able to do 100 miles an hour, but it's probably most efficient somewhere around 50 miles per hour. Speaking of cars and efficiency, let's shift gears and talk about motors. This will be the first of several discussions we'll have about motors, so we'll just lay the groundwork right now. When we talk about motors, there's two things you have to keep in mind. First, we have the shaft power. So power out is equal to power shaft, typically expressed in horsepower. Is not to be confused with power in, which is electrical, typically expressed in kilowatts. Know that horsepower may be expressed in terms of torque. For this class, we'll use foot-pounds and RPM. So torque by RPM divided by 52. 52 gives you horsepower. That's torque and velocity. 1 horsepower is equal to 746 watts. And remember, efficiency is power out over power in. If you put all those concepts together, you're in good shape to talk about motors. For example, you're given a torque of 588 foot-pounds, a rotational velocity of 1785 RPM, a power in of 176 kVA, and finally a power factor equal to 88% inductive. If you put these two together, you can find your power out. If you put these two together, you can find your power in. And at this point, it becomes a bookkeeping problem. So we put our power out on this side. We're going to put our power in here. Oh, I forgot to tell you, didn't I? We're looking for efficiency. So find efficiency of this motor. Horsepower is equal to 588, so that's torque by RPM, all divided by 5252. 58, that's 588 by 1785 divided by 5252. It looks like this is a 200 horsepower motor. Quick conversion to kilowatts. So using dimensional analysis, 746 watts to 1 horsepower. We come over here and we cross off the units. We're left with a power out of 149 kW. On this side, we start with a power triangle, 176 kVA. We know that the power factor is the ratio of real power to apparent power. So 0.88 is equal to P over 176 kVA. So power in is equal to 155 kW. Put those two together. The efficiency is equal to 149 over 155, or simply 96%, which isn't bad for this large 200 horsepower motor. Here's another example. This is a three-phase system, and we're asked to find the line current. The solution goes something like this. We first calculate the power triangle for the entire system. We then break it into 3 smaller triangles, representing the power in each of the phases. We'll then solve for the line current on a per phase basis. Starting with the output power, say 50 horsepower, we multiply that by 746, which tells us that power out is equal to 37.3 kW. Efficiency is equal to power out over power in. So that's 0.93 is equal to 37.3 kW over power in. Our power in is 37.3 divided by 0.93. So that's about 40.1 kW. We can now make our power triangle. So that's 40.1 kW. Our power factor is 80%, so that's 36.9 degrees. And remember that power factor is the ratio of real power to apparent power. So 0.8 is equal to 40.1 over S. So 40.1 divided by 0.8 tells us that this is 50.1 kVA. So S we would express as 50.1 kVA at a phase angle of 36.9 degrees. And we make a big note here. This is the big triangle that we need to divide by 3 to do a per phase solution. So S phase is 16.7 kVA at a phase angle of 36.9 degrees. Schematically, we now have something that looks like this. On a per phase basis, we have some line to neutral and it is supporting a 16.7 kVA load at an angle of 36.9 degrees. That voltage is 460 divided by root 3, which is 266 volts. We'll assume that's at an angle of 0 degrees. So S is equal to VI complex conjugate, solving for the complex conjugate of the current, 16.7 kVA, phase angle 36.9 degrees, all divided by 266. The line current, which is right here, that's the thing we were looking for, is about 63 amps at a phase angle of negative 37 degrees. So if we would use a clamp ammeter like so, it would measure about 63 amps. Let's finish our discussion with a bit of vocabulary. Polyphase AC motors. Typically three-phase. Come in two varieties. We have the induction motor and we have the synchronous motor. Of the two, the induction motor is the most popular. Each of these motors has a unique speed-torque relationship. We'll let this be speed, typically in RPMs. We'll let this be torque. A typical induction motor has a curve that looks something like this, whereas the synchronous motor, with this being speed, and again torque, is just a line. This line, this speed that never changes for changing torque, occurs at what's called the synchronous speed. The induction motor also has that point, but it turns out that the induction motor produces no torque at the synchronous speed. So NS is the synchronous speed. Mathematically, the synchronous speed is defined as 120 by the line frequency divided by the number of motor poles. For now, think of the number of poles as a description of the rotor. This is an example of a 2-pole rotor, and this is a 4-pole rotor. Here the word pole describes the magnetic field. So a 2-pole rotor will have a north and a south pole, whereas a 4-pole will have a north, south, north, south. So it'll have 4 poles. These can be permanent magnets, but they're more likely to be electromagnets. So you'll find coils of wire wrapped around like so. And here you'll find coils of wire as well. I'll leave a link in the comments below for a video which clearly shows the construction of the rotor, where you can see the individual wires as they're wound around the poles. As we wrap up this discussion, let's look at how this equation is used. Consider the Hoover Dam. There you'll find a 60 Hertz machine that has 40 poles. Find the RPM. So the synchronous speed is 120 by F divided by the number of poles. So the synchronous speed is 120 by 60 divided by 40. That's 120 by 60 divided by 40, which gives you a synchronous speed of 180 RPM. This equation describes the speed at which the generators are turning at Hoover Dam.